So in the last session we have discussed LP problems. Now today we specially discuss LP problems where the feasible region is unbounded. We had last example about LP problem where the physical region was unbounded. Now today we discuss theory related to it and some more examples. So we have this objective function. We have z equals to ax plus by. This is objective function. So what we do, graphically you get the corner points that we know. Graphically get the corner points. Then you put all the coordinates of the corner points in the function. So suppose maximum value of z, we call that as big M. Maximum value of objective function, we call that as a big M. And minimum value, we call that as a small m. Minimum value of z equals to small m. Maximum value we call big M, and minimum value we call the small m. Okay, now if feasible region is unbounded, then we need to do this one. What we do, if you are asked to maximize the function, then determine half plane by this line ax plus by. Maximum value is this, greater than m. So you draw this inequality. Which inequality? Ax plus by greater than m. If you are asked to minimize the function, let me write here, then you determine this half plane. Determine half plane by same objective function ax plus by. What is the minimum value? Small m. So less than small m. Less than small m here. So maximum value then greater than big M, that was maximum. And if you are asked for minimum value, then less than small m. Right? That's the difference. I repeat, if you are asked for maximum value, you see maximum value, then greater than m. And here less than m. Okay. Now this is a concluding line from this. What's the concluding line? If the half plane and the feasible region has no common point, this half plane and that feasible region, which you already did, feasible region has no point in common, I repeat what it says. The half plane and the feasible region has no point in common. Then maximum value of z equals to m, which you did in the beginning. Otherwise means what? If they have common points. Otherwise the function z has no maximum value. Maximum value doesn't exist. I repeat this portion, what it says. You determine this half plane. Which half plane? Ax plus by greater than m. What is this ax plus by? This objective function. Now half plane and feasible region which already drawn in the beginning to get the corner points. has no common point, no point in common, that means it has no common point, then the maximum value is this m which you have stated earlier. Otherwise, what's the meaning of this? It means if it has some common point, then z has no maximum value. Z has no maximum value. Otherwise, z has no maximum value. This was last example of the last session. Now come to this. Same procedure here. Half plane and feasible region, and the feasible region has no point in common, conclusion is same. Then here there we wrote the maximum value, here minimum value of z equals to small m. Otherwise function z has no minimum value. I repeat this. What you need to do, you get the half plane by drawing this inequality. This is for minimum value, ax plus by less than m. For maximum value, it's greater than m. So we'll get the half plane by the inequality, feasible region. If these two regions have no point in common, then the minimum value is small m, remember, which you had stated earlier. The minimum value is small m. Otherwise means what? If they have a common points. Otherwise means what? If they have a common point, then function has no minimum value. This is a theory especially for unbounded region. Now we do two more examples, one for maximum value and one for minimum value, so it will be clear to you. Started with exercise 12.1, fourth question. This is the objective function which is to be minimized under these two constraints. This is non-negative condition. This says that solution region will be in the first quadrant, which we know now very well. Okay, so we represent this inequality graphically. We represent inequalities, which are the constraints, graphically, these two, and get the feasible region. Now you know how to do this. Indirectly it is x plus 3y equals to 3, and the other one is x plus y equals to 2, equals to 3 equals to 2. How do we do? We prepare this tabular form. X is 0, y is 1, y is 0, x is 3. You know x and y here. If x is 0, y is 2, y is 0, x is 2. Fine. This is just to draw this. So I'm drawing this now. Okay, so we are concentrating here. This is origin, 0 then 1, so this point, 3 then 0, so this point. So we have this line through these 2 points. This is nothing but which function? X plus 3y equals to 3. Now whether it is this half plane or this half plane, how will decide this? As we did in earlier examples, put 0 0 in the inequality. We check for this. 0 plus 0 is greater than or equal to 3, not possible. That means this is above region, so I'll just put arrow. That means we concentrate over here. This is the region for this first inequality, not the lower region, because origin doesn't satisfy. 0 plus 0 is greater than 3. 0 greater than 3 not possible. That means this not lower region. Above region is the solution for this inequality. Now we are drawing the second one. There 0 then 2. So here. And 2 then 0. So this point. So we draw line through these 2 points. We draw line through these 2 points. So this is the line passes through these 2 points. What is the equation for this? Which is x plus y equals to 2. Now again, whether it is this region or this region. For first line, it is above region. What about this? Above region means this is also included. What about the second line? Check for 0, 0. 0 plus 0 like this. 0 plus 0 greater than or equal to 2. Is this possible? No. This is not possible. That means not this region where the origin line is not the required region. So above region. So above this green line. Above this green line. Above this pink line. And in the first quadrant. So this is the required region. In the first quadrant, remember. Why in the first quadrant? Because you see you have non-negativity condition, this one, right? Therefore only in the first quadrant above these 2 lines. Now this is unbounded. What are the corner points? 1, 2 and 3. I hope this is clear to you now. These 2 corner points are obvious. If I call this as A, then here 3, 0. B we need to find. We call this as C, which is 0, 2. So corner points are, if I write corner points, so one is A, which is 3, 0. It's obvious from the graph. B we need to find. What about the C, which is 0, 2? Right? 3, 0, 0, 2. You know this. Now how do we get the B? That is solving those 2 equations. So we write for B, solving equations. Solving which 2 equations? Solving x plus 3y equals to 3 and x plus y equals to 2. Just to put the minus sign here. If I put the minus sign, x will get cancelled. So you will get the 2y equals to, here 2y equals to 1. So therefore y is half. What is y? Which is 1 by 2. And put the value of y in any one of these 2. If I put half here, so therefore x will be, what is x? It will be obviously 3 by 2. Just we have solved these 2 equations by elimination method. So I'll write here only. Therefore coordinates of B will be 3 by 2, 1 by 2. This is B, this is C, and this is A. Now we prepare the table. You know whether it is a bounded region or unbounded region, you need to prepare the table. So here I'll write corner points and we write the value of function, value of the objective function z, which is given by which expression here? 3x plus 5y. Okay, so one corner point is A. What is A here? A, you know, 3, 0. A is 3, 0. What is the value of the function? 3 3 is 9 and this is 0, so 9. The B is, 3 by 2, 1 by 2. So this will be here 9 by 2 and this is plus 5 by 2. So 14 by 2, which is just 7. And C, what about C? 0, 2. So 0 then 2, it will be 10. Fine. So we have this table form for the corner points and the value of the function here. Now you are asked to maximize or minimize the function. You are asked to minimize. So this is the minimum value, which is small m as per our theory. Small m. Okay, now if you have bounded region, then this is the required minimum value, but region is unbounded. So what we do now, just look at it theory. For unbounded region, we draw, what we draw? objective function 3x plus 5y for minimum value less than 7. Just I'll show you. See, if you have minimum value of z here, small m, then we draw this ax plus by less than m, and we find the half plane. We are following this theory. Okay, so I'm drawing this in the previous slide. So I'll prepare the table. If x is 0, then y will be 7 by 5. If y is 0, then x will be 7 by 3. So we represent this 0, comma 7 by 5. 7 by 5 means 1 point something. So it will be somewhere here. Fine. This is 0. Here you have 0, 1 point something. What about this? 7 by 3. It is roughly 2 point something. 2 point say 5 comma 4. So somewhere here. 2 point something. Roughly over here. Now we draw a line through this. So we usually represent this by dotted line. Okay, we normally represent this by dotted line. This is for that objective function. This is which function? It is nothing but the 3x plus 5y equals to how much? 7. Okay, now this dotted line has two half planes. One is lower half plane and the other one is upper half plane. Right? This is very important part now. Be careful. One is upper half plane. I'm talking about this black dotted line, and the other one is lower half plane. Now, how do we decide half plane? What we have written in the theory? What you have written in the theory? Half plane determine half plane by this. So we are finding whether it is lower half plane or upper half plane. This half plane or this half plane. How do we check that? Take origin again. I'm taking origin. Check whether origin satisfies that inequality or not. Check whether origin satisfies that inequality or not. Where is inequality here? 0 plus 0 less than 7. 0 plus 0 less than 7. You can see here 0 plus 0 less than 7. Is this true? Yes. That means the half plane that contains origin is the required half plane. So this is the required half plane. This is the half plane. I hope this is clear to you. The half plane determined by that inequality. Which inequality? This one. Is this lower half plane. And the unbounded region was this green half plane. Do you have any common point between these two? Do you have any common point between these two? No. There is no common point. So what we have written? If the half plane and the feasible region has no common point, then the minimum value is that small m. So I'll write now, therefore half plane and feasible region has no point in common, and therefore as per that theory, therefore the minimum value of the function, minimum value of z equals to the minimum which you had stated again, which is 7. Fine? Is it clear to you? This is very important. And where that minimum value is obtained? At 3 by 2, 1 by 2. This much you need to. This is extra thing when you have unbounded region. If you have bounded region, then this is a minimum value, finished. But if you have unbounded region, you draw this inequality, get the half plane, see whether there is a point common in half plane and a feasible region or not. Here, look at this slide. There is no common point in these two, and therefore this is the minimum value of the function. Fine? We do now 9th question in the same exercise. Maximize this function minus x plus 2y subject to this 4 constraints: x greater than or equal to 3, x plus y equals to 5, x plus 2y greater than or equal to 6, and y greater than or equal to 0. So we One, we have x equals to 3 line. You know here y variable is absent, so this is parallel to y axis, so this is a vertical line through 3. Then what about this? X plus y equals to 5. So there you can have the table. If x is 0, y is 5. If y is 0, x is 5. So you have 0, 5, 5, 0. What about this? X plus 2y greater than equals to 6 here, just to draw the line. So we prepare the table here. If x is 0, y is 3. And if y is 0, x is 6. So 0, 3 and 6, 0. Then one more, that is y equals to 0. You know this represent x-axis. X variable is absent, so parallel to x-axis through 0. So it has to be x-axis. This is x-axis. Here we draw the lines. And this is a vertical line parallel to y-axis because y variable is absent. You know all these things. Now we represent these 4 inequalities and we try to find the common region. So this is a Cartesian plane here. First line through 3 parallel to y-axis. So it will be this line. This represent which line? X equals to 3. Now here x is greater than or equal to 3. So value of x should be more than 3. So this side region, right side region, not the left side region. X is more than 3. So this right side region, not the left hand side region. So we keep this region in our mind. Okay. So then 0, then 5. 0, then 5 here. Then 5, then 0, which is here. So second line will be this. This is second line. Through 5, 0 and 0, 5. This one. So here we have x plus y equals to 5. Now we decide whether it is this region or this region. So we check for 0, 0. Check whether 0, 0 satisfies this inequality or not. 0 plus 0 greater than or equal to 5. Is this possible? No. So the region that is 0, 0 side is not the required solution. We go for this region. So up to this it is this region. Right side of the green side and above side of the second inequality. Not this lower region. That should be clear to you. Okay. Third one. 0 then 3. We'll go for third now. 0 then 3. This one. 0 then 3. That is this one. And 6 then 0. So this line. So line through these 2 points. This is third inequality, which is x plus 2y equals to 6. Now again decide whether it is this region or this region. For previous 2 it was this region. Now check for 0, 0. What about 0, 0? Will it satisfy this? 0 plus 0 greater than or equal to 6. Again not true. So the region that is 0 side is not the required region because it doesn't satisfy this inequality. So above region. So up to this it is this region. And finally now which line? X-axis. So this is x-axis, you know. This one. This one is the x-axis. This is nothing but which line? Y equals to 0. Now here it says that the y should be greater than or equal to 0. So value of y should be positive. So upper side. So by just combining all this, we are getting this as a feasible region. One point over here, the other point over here, and one more over here. Right. These are the 3 corner points above x-axis, this region. This is unbounded feasible region. This is unbounded feasible region. How many corner points? 3. 1, 2, and 3. This I'll call A, which is 6, 0. This we need to find this we need to find. So these are the three corner points, A, B and C. What are the coordinates of A, which is obvious, which is nothing but what? 6, 0. Coordinates of A are obvious. So corner points now. Corner points. So one is A, which is nothing but the 6, 0. B, how do we get the B? It is intersection of these two, you can see. So for B, I'll write on the next slide. For B, solving these two equations. So for B, solving x plus 2y equals to 6 and x plus y equals to 5. We just solve these two equations. So I'll just put the minus sign here. So I'll get the y, x will get cancelled. This is 1. So y equals to 1. If y is 1, put any one of these two. So x will be 4. And therefore b will be 4, 1. B will be 4, 1. Now for C, look at C. C is intersection of which two? It is intersection of x plus y. This line and x equals to 3. X is 3, put here. So y will be 2. So for C, I'll write. For C, this was for B. Solving which two equations? Just look at it graph. X equals to 3 and x plus y equals to 5. If x is 3, place here, so y will be 2. And therefore coordinates of C will be 3, 2. This is C. Here we have B. Okay, now we prepare the table. Now we got the coordinates of all the corner points. So we just prepare the table. So let's see that. So we prepare this table, 6, 0. So here minus 6 and 0. So value is minus 6. 4, 1. Minus 4 plus 2, which is minus 2. 3, 2. Minus 3 plus 4. So it is just 1. If you just look at the question, you are asked to maximize. So this is the maximum value, and which will be capital M as per our theory. Right? Maximum value. Maximum, which is nothing but the big M, as we were discussed. Now your region is unbounded. So what we do? We draw now, just refer the theory. Draw the region. Which region? Objective function. Minus x plus 2y greater than M. What is M? Which is 1. Just have a look at the first slide. You will realize if M is the maximum value here, then you see this greater than M. We are drawing this, and now we'll find the half plane. So we are drawing which inequality now? Objective function minus x plus 2y is greater than M. We draw this. We are going to draw this inequality, and let's see which half plane. So I'll prepare the table here just to make it easy. If x is 0, what is y? 1 by 2. Imagine equality here. If y is 0, let me put 0 here, then x will be minus 1. So I'm drawing this 0, 1 by 2 and minus 1, 0. And let's see which half plane can be obtained. So first point is, which is the first point there? 0, then half. 0, then half, it is here. 0, then half, it is here. And next point is minus 1, then 0. Minus 1 is here. So if you just represent this by line, it would be like this. I'll show by dotted line. You can extend like this. Now here, this represent minus x plus 2y equals to 1. This dotted line. Now which region? You take, suppose this, take origin. Where is the inequality here? 0 plus 0 greater than 1. Is this possible? No. So the upper half region. Upper half region means this one. This one is the region determined by this half plane. What you have noticed? Is there any common point between these two? The feasible region and the upper half plane? Yes, these all are the common points. You can see these are all common points. These are all common points, right? So I'll write in the next line the half plane determined by the above inequality, and therefore I'll write half plane and feasible region has common points. There are many common points, has common points, right? Is it? And therefore the function has, as per our theory, let me write z, has no maximum value. You are asked for maximum value. Function has no maximum value, right? See, again I repeat, this is the half plane above region and this is the feasible region. There are common points. These are all common points. You can see these are all common points. So you have some common points. So feasible region and half plane have common points, and therefore function z has no maximum value as per our theory. I hope now you are clear whenever you have unbounded region. I'll go to 10th question in the same exercise. Maximize this objective function subject to these two constraints with this non-negative condition that is in the first quadrant. So we just prepare the table for first one. I'll write equals to -1, your x and y. If x is 0, you know here y will be 1. If y is 0, x will be -1. For the other one, minus x plus y equals to 0. I'll prepare again table just to draw the straight line. If x is 0, y is also 0. Now you cannot take again here 0. Then again you will get the same point. So I'll take 1 for example. Any point you can choose. If x is 1, then what about y? Obviously it is 1. This is actually y equals to x line. Very standard line. Y equals to x line bisecting which quadrant? First quadrant, you know. Okay, so we represent this in the Cartesian plane, and we will see what is the feasible region here. Okay, so in the first quadrant, if x is 0, y is 1, so this point, and -1 then 0, so somewhere here, -1 then 0, -1 then 0. So you will have this line passing through these 2 points. We are interested in first quadrant. This is equation of which line? You know it represent x minus y equals to -1. Now let's decide the region, whether it is this region or above region. So check for origin. What about origin? Will it satisfy this? Origin here 0, in the first one we are putting here, plus 0 is less than or equal to -1. Is this possible? No. So this is not the required region. This is the region, above part. This is the region in the first quadrant. So this is our solution region for first one. Let's go for the second one. 0, 0, it passes through region. Then 1, 1, so it is this point, 1, 1. So we'll have line like this. Both are parallel lines. If you observe for a while, these two lines are parallel. They will never meet. Remember, this is which line? Slopes are equal, you can check. Minus x plus y equals to 0. Now here you cannot check for origin. So I'll take this point. You can take this point. You can take this point. Any point you can take from the region. Suppose I have taken 2, 0 here. I'm putting 2, 0. X is 2, y is 0. Is this less than or equal to 0? Yes. So this is the required region because 2, 0 satisfy this. So here required region is this side. Here required region is this side. Remember, this is the required region. So do you have common region here? No. There is no common region. We had such questions in even 11th standard also. Do you have any common ration in these two? No. So therefore we say that there is no feasible ration. Feasible means common or possible ration. Feasible ration. There is no feasible ration. And therefore, once there is no feasible region, you cannot get the corner points, and therefore Z has no maximum value. Maximum value cannot be obtained. No maximum value. Function, objective function has no maximum value. I repeat, there is no common region. That means there is no points which satisfy both the inequalities. So function has no feasible region, and therefore you can say that the objective function Z has no maximum values. Maximum or minimum value can be obtained only when the function has feasible region and the corner points. Your function has no feasible region. Fine. Now I did 3-4 questions from this 12.1. Remaining you can try. Not a big task, right? So try for remaining questions of 12.1. Right? I did 4-5 questions from there. Unbounded region should be clear to you, and I have taken both the questions. For remaining all questions, you have just bounded region. Get the corner points, prepare the table, and decide maximum or minimum value, as I did in the previous session. Now exercise 12.2 and miscellaneous exercise. Both the exercises about those practical questions. So you have some data and you convert into LP problems, right? These two exercises are not important as far as the examination point of view, but still if you are interested, I'll show you 1 or 2 questions how to reduce into LP problem. That is how to find the objective function, how to form the constraints. So for that, just for your information, I'll come to first question of 12.2. You see, I'm trying to express the given data in form of table, right? So question talks about 2 types of the food. So we have here food P and Q, food P and food Q. I'm expressing the given data in form of table. Reshma wishes to mix 2 types of the food P and food Q in such a way that the vitamin contents of the mixture contains at least 8 units of vitamin A. So I'll write here, we have vitamin component. So I'll write here vitamin A and vitamin B. Fine. Okay. Now if you read further question, the food cost 60 rupees per kilogram, Q 80 rupees per kilogram. Food P contains 3 units per kilogram. So here 3 units per kilogram of vitamin A and 5 units food P contains of vitamin B. So this information are about vitamins. Read further. Food Q contains 4 units of vitamin A and 2 units of vitamin B per kilogram. Okay, now what is the minimum requirement? So I'll write here a requirement. Let me write here requirement. What's a requirement? It's given in the beginning. The mixture contains at least 8 units of this vitamin. So minimum 8. So total units should be 8 or more than 8. Requirement minimum 8, at least 8, and 11 units of vitamin B. So this is 11. Fine. So we introduce 2 variables. Now let's write one variable x here. Variable x, that is nothing but x kilogram of food P. There are 2 foods. And y kilogram of food Q. let x be kilogram of food P. Why we have taken x and y for this? Because you read the question, right? Mix two types of the food P and Q. Mix two types of the food. So we take one type as x, the other type as a variable y. You just read the first line. Mix two types of the food P and Q. So I've taken variable x for food P, variable y for food Q. Fine. Now what you want to minimize? Determine the minimum cost. In every LP problem, either the minimization or maximization. So our objective function is about the cost. Objective function is minimize z equals to cost. Now what is the cost here? Let me write cost. Cost is how much? Read the question. For food P, it is 60 kilograms. So I'll write here 60. And it is 80 kilogram for Q, right? This is about these two foods, food Q, food P. This is vitamin A, vitamin B. Now, per kilogram, we have taken X kilograms. So total cost for food P will be 60 into X. Is it? Am I right? Is this clear to you? And what about for the other one? Plus 80, that is per kilogram for Q. How much kilogram we have introduced Y? So total cost for food Q will be 80Y. So this is the total cost. 60x plus 80y. 60 per kilogram, 80 per kilogram, x kilogram food P we have chosen, y kilogram food Q we have chosen. So total cost for food P 60x, food Q 60y. This is the cost, which is obvious, and it has to be minimized because the question is what? Minimize the cost. So minimize that equals to this. Subject to, so now subject to which constraints? Total vitamin should be. Now x units of food P used. Fine. X units of food P is used. So 3 into x plus y units of Q is used. So 4y must be greater than or equal to 8. For vitamin A, remember, this constraint is for vitamin A. Minimum 8 units should be used. So total units of vitamin A. And same way for vitamin B. X units for food P, Y units for food Q. So this way horizontally will form. So we have 5x plus 2y. This is total vitamin B and minimum should be 8. So greater than or equal to 8. And kilograms never be negative. So x must be greater than or equal to 0. Y must be greater than or equal to 0. This is the formulation of LP problem. Right? Now this become LP problem. Minimize this objective function subject to these constraints. Not a difficult task. The formation of LP problem is very important if you just write data in form of table. See, this row is specially for vitamin A. This row is for vitamin B. We have introduced variable x for P, variable y for Q. So 3x plus 4y greater than or equal to 8. Minimum 8, remember. That's why we have written greater than or equal to 8. Vitamin A should be 8 or more than 8 units. Vitamin B should be 11 or more than 11 units. Number of kilograms never be negative, so greater than or equal to 0. And in the question itself, it is written that the minimum cost. So minimize the objective function. This is the total cost. Per kilogram for food P is 60. We have x kilograms, so 60x. Per kilogram for food Q, it is 80 rupees. So 80 into y. So this is the cost function. So objective function, and these are the constraints. Now you solve further as we did in the earlier exercise. The only important in this exercise is 12.2 and miscellaneous is this formulation of LP problem from the given data. Fine. Now how do we do further? As we did. So that you can do. Draw the graph, get the corner points, find the minimum value. So I'll get the minimum cost. So try for some more question if you wish to do right now. Otherwise, once the syllabus gets over, I'll do questions of 12.2 and miscellaneous for you, remember. Right now it's not important, right? So now from the next session, we'll move to the next chapter.